In our previous lessons, we were working with relationships of right triangles and their side lengths. In particular, we were looking at Pythagorean triples. Remember, those are the integer side lengths where the sum of the two legs squared is equal to the hypotenuse squared, and we found very specific values that made those true. 3, 4, 5, 5, 12, 13, and so on. We also looked at your right isosceles triangles and found a pattern that exists with those. They're also referred to as your 45, 45, 90 triangles. We know that the leg times the square root of 2 is equal to the hypotenuse. Conversely, if we were given the hypotenuse, to undo it to find the leg, we could divide it by the square root of 2. So let's look at a couple of example problems. If we have an isosceles right triangle with leg lengths of 9, what would be the length of the hypotenuse? Let's get a visual. So here is our isosceles right triangle. Isosceles because the two legs are congruent and we have the right angle. There's our right. So again, what's the pattern that we remember? In a isosceles right triangle, a 45, 45, 90, the leg times the square root of 2 is equal to the hypotenuse. So, do we know the length of the leg? Yes, we do. It's 9. So if I take the length of the leg times the square root of 2, that gives me the hypotenuse. So what's the length of the hypotenuse? That would be 9 square root of 2 units. Well, how about this one? If we have an isosceles right triangle with leg lengths of 4 square roots of 5, what would be the length of the hypotenuse? Again, let's get a visual. Here's our isosceles right triangle, and the lengths of the legs are labeled as 4 square roots of 5. Now, what's the relationship between the leg and the hypotenuse for these types of triangles? They have that ratio of the square root of 2. So the length of the leg times the square root of 2 is equal to the hypotenuse. So the length of the leg is 4 square roots of 5. If I multiply that by the square root of 2, that will give me the length of the hypotenuse. So we know that we can condense the two square roots into one. So if I think of that as the square root of 5 times 2, that's the square root of 10. Does 10 have any perfect square factors that we could simplify? It does not, so we're going to have to leave it as is. So the length of our hypotenuse would be 4 square root of 10 units. If we have an isosceles right triangle with a hypotenuse length of 3, what would be the lengths of the legs? So let's get a visual. Here's our isosceles right triangle with a hypotenuse of 3 units. How can we find the length of the legs? Well, again, remember, the ratio is the square root of 2 from the leg to the hypotenuse. So the leg times the square root of 2 is equal to the hypotenuse, and our hypotenuse happens to be 3. We need to undo this equation to solve for the leg. So since we are multiplying by the square root of 2, to undo that, we would divide each side by the square root of 2. We know on the left-hand side here, the square roots of 2 will divide out. On the right-hand side, we'll now have 3 divided by the square root of 2. Now, we know when we're working with radicals, we don't want a radical in the denominator. We want to make sure it's an integer value that we understand how to break it into those parts. So at this point, remember, we have to work on rationalizing the denominator, where we take this value and multiply it by a useful form of 1, so we no longer have the radical in the denominator. Well, what would be a good useful form of 1? It would involve the radical within the denominator. So if I multiply this by the square root of 2 over the square root of 2, that has a value of 1, that will help me get a number in the denominator that I know how to work with. So again, how do you multiply fractions? You multiply across. So the numerator, we would have 3 times the square root of 2. And in the denominator, what would happen? Well, there's a couple ways to think about this. We could write this as one radical, the square root of 2 times 2, which is the square root of 4, and we know that's a perfect square that has a value of 2. Or again, you're recognizing that you're taking a radical times itself, that would undo itself, right? Because it's saying like you have a radical squared. Those are inverse operations. And because they undo, you also know that your answer is 2. Regardless of the path that you take, your denominator is 2. So what's the length of the leg? The leg is now worth 3 square roots of 2 over 2 units. Now you're going to be working with more special right triangles, finding their missing side lengths using the patterns that we've done up to this point with Pythagorean triples and also with your 45, 45, 90 patterns, your isosceles right triangles.